We can now create a list of waypoints that we want the robots to go. I do this here in the beginning where I set other constants, and we can call this list WP for waypoints, make it a list, and then we can add tuples into it. To find out where we need to go, we can grab the ping pong ball and see where it actually ends up. And in this case, the ping pong ball is at something like 0 and 0.68. So we can enter these values here and then select the next waypoint, which might be here, and we get 0.44 and again 0.68. Then we will move the waypoint here, 66 and 0.51. And let's just add one more waypoint, and the rest you can do on your own, but this will require the robot to go around and turn 180 degrees, which is something we would like to see. And this is 0.3.5 and 0.24. Alright, now we define a variable index to index the waypoints, and I would like to set this to 1, so we are indexing this waypoint. Now we can think about an arrow, and in order to visualize this, we should go ahead and actually set our marker to the position, and the set single field vector 3f, and we want to grab the waypoint at index, and here I unpack the tuple into numbers and then grab the last entry, which should be 0, and turn the whole thing into a list. So we provide a list of 3 floats to this function. Let's try this real quick and see whether the ping pong ball ends up at waypoint 1. And yes, it's here. Now what we can do is we can compute the arrow. Now the arrow is both distance and angle, and we can start with the distance. And for this we will choose the Euclidean distance and call this rho. The Euclidean distance is the square root of the squared differences between the x and y position. So we have the x position of the robot, and we have the y position of the robot, and I square both of these. And now we subtract from this the waypoint's x position, which is the first entry of the tuple, and then we do the same for the y position, but this time it's the second entry of the tuple. So this should give us an arrow in distance, and we can print this to see how this looks like. Of course, we need to add these things. This is not a list. We have to add the 2 squares, and so we have these 2 components, and now this should work. And there it prints an arrow, and as we expect, the arrow is going down as we are approaching our waypoint. Now what should happen to the arrow? It should go down to 0, and it indeed does that. So as the robot arrives here, we are very close to 0. Of course, the ping pong ball itself has also a diameter. Now what about the angle? Let's start the simulation again so we see the ping pong ball. So we can see that the robot should effectively turn a little less than 45 degrees in order to directly drive to this waypoint. So you see what I mean? The current direction of the robot is going straight. It has to do a right turn, which would be a negative rotation based on the direction of rotation, and it is a little less than 45 degrees because this laser scanner is 45 degrees. Now, how do we compute this? One way of doing this is to again use the arcus tangens and look at the distance between, or the error in the x direction and the error in the y direction. And of course we have to do this in the world coordinate frame. So the robot is already looking straight up, but the world coordinate frame we see down here. So this means this is the error in x and this is the error in y. Alright, where do we get that from? We have written something like this here, but we have to be careful because this is not the right sign. We can see this in a second when writing down an expression for the error. Let's call it alpha, and we use again the arcus tangens function from NumPy, and when you look this up you will see you have to first provide the y and then the x dimension. Alright, so what's the y dimension? The y dimension is the index, the waypoint at the index first entry, and in this case we expect the y to be positive, so we can subtract the actual position of the robot. And we do the same for the x direction. We grab it here. So you can see here the x direction is positive in this direction, and so we have to subtract the actual position of the robot. Now if we print also the angle here, we should see something. And so what happens is the angle gets smaller and smaller, and as we approach the goal, the angle ends up to be almost 0. So the robot has the waypoint at 0 degrees to its right. Now this is all very difficult to translate, so let's divide this by pi and multiply it with 180 so we get a better grasp on what's going on here, and print this. So we see the ping pong ball is at around 53 degrees, and as the robot goes closer the ping pong ball is at a smaller angle, and finally it is at 0 degrees. Now 0 degrees is the heading in the world coordinate system. The robot itself already has a heading which we can print as well, and I already have this here, so let's uncomment this and see what the robot is actually headed at. So the robot is already heading at 1.57, which is 90 degrees. This makes sense. When you look at the x-axis, it is turned by 90 degrees to the left. Now, what is the desired angle of the robot? The robot has to turn by around 35 degrees to the right. So the actual error should be the angle at which the ping pong ball is minus the current orientation of the robot. So let's subtract theta here, and now let's print again what the error is. And let me just remove rho here because it makes it harder to read. And let's see whether we will get an angle that is in the robot coordinate system. Alright, so it says the robot should turn 37 degrees to the right, so minus 37, and as it goes closer this angle is increasing as the robot has to turn harder, and at the end we expect the robot to have to turn 90 degrees. Now what happens when I keep turning, because I'm actually now turning due to the line following, I do turn in the right direction, the angle gets smaller, and now the error in angular direction is close to 0. So this looks quite promising. We now have expressions for an error in distance, and we have an expression for an error in heading. And I say heading because I want to use this later to actually turn the robot in the right way and drive in the right direction. So to test this further, we should implement something that advances the waypoints as soon as the robot gets too close. How can we do this? We already know how close it is, And so we could say something like, if rho, the error, is smaller than, let's say, 10 centimeters, we can actually index it to the next waypoint. So let's think about this real quick. This should work, and now we can run the simulation and see what happens. So let's do a little fast forward here, and maybe we should turn off the sensor rays at some point to make this faster, but for now that's fine. And now as the robot gets closer, the ball is jumping to the next waypoint that we have defined, and then when it goes to the next one, the simulation will crash, as we haven't really taken care of preventing this field from overrolling. Okay, so this is fine, but now what we should do is we should actually turn off the light array points so we get a little bit faster simulation. Now let's look closer at what actually happens with the angle heading error, which is already in the robot coordinate system. And as you can see, once the robot is turned the right way, it becomes 0. But now let's see what happens at the next waypoint. What should we expect? The robot again has to do a right turn. That means we expect a negative heading, and indeed we have something like minus 27 degrees here. As the robot turns toward the waypoint, this arrow goes down. Now we should have something around minus 90 degrees, and yes, we do. And as the robot turns, the arrow gets smaller. So far so good. So we can now go and try to actually implement a controller for this.